Okay, this is our last segment on stellar evolution. Basically, we're going to come on to high mass stars. So, just like all of the stars, they leave the main sequence when they run out of hydrogen in the core, and basically for the first few steps, it's very similar to what happens with low mass stars, except that they always stay very bright. Remember that the highest mass stars are already up at several times higher than a solar mass star, and they stay up at that supergiant level for luminosity. But basically, first of all you have a hydrogen burning shell and a helium core, and then the helium switches on, but it's never going to be degenerate, you won't see a flash. And then you're going to have the helium shell and the carbon core, but that won't flash either. And then you'll have the carbon shell, and so on. And so basically what we get is it's going to continue following that phase of going through successive red supergiant phases. So it goes from a blue star to a red star, then it goes back to blue again, then red again, then blue again, then red again, as it switches on each successive core burning. So it just eventually runs out of material, and we'll get into why it explodes as a supernova. And basically, so this is kind of the schematic of what's going on. We've got hydrogen burning, and that ignites at a few million Kelvin, and it lasts for a few million years. This is for a 25 solar mass star. Then you have helium burning, which makes carbon and oxygen, ignites at a higher temperature, and lasts for less than a million years. Then you've got carbon burning, which makes neon, sodium, magnesium, and oxygen. Remember, we talked about having some white dwarfs that are made of these compositions. And this happens at an even higher temperature, 600 million Kelvin, and it's going to be at only lasts for 600 years, because remember, for each one you've got to take 12 of these to make one of these, so you've got a lot less of these carbons, and to keep that high luminosity, you're getting less, the E equals MC squared equation, you get less energy out of each of these, and so you have to burn it really fast to keep that high luminosity. Here also, notice that you don't need a very high mass object to get helium burning, so that's even things that don't go past hydrogen burning. For helium burning, you need to be a little bit more massive. I would say it's actually 0.8, not 0.4. And then to get to carbon burning, it's actually bigger than this, it's 0.8. Remember, these coming from textbooks, and they're not always correct. And then you need to be up around 8 solar masses to start with in order to get the next step. So the next step is you've got neon in the core, and when you burn it you get oxygen and magnesium. The next step is you've got oxygen in the core, and you get silicon, sulfur, and phosphorus. And then we've got silicon in the core, and when we stick those together we get iron and nickel. But you have to actually go to very high temperatures in order to get this to happen, and so that's why you need those heavier elements. And this is just kind of giving you an idea of the different things that can happen. So I've got a carbon here, but if I add on a hydrogen, I get nitrogen 13, which is unstable, that gives me a carbon 13, and then I might add on a helium to that, and that gives me an oxygen 16, because it decays. And so you've got all these different things that can form and different patterns that you can go in. So you actually make all the different isotopes. And so for a star of about 25 solar masses, this is again telling you how long so it spends 90% of its life as a main sequence star burning hydrogen. And then the time gets less and less until when the core is made of silicon, it's only got enough silicon to fuse for one day, and then it will explode. The problem is we can't see the inside. So you can see here, this is slightly more complicated, that we've got an iron core, we've got that's not burning, we've got silicon fusion, magnesium fusion, neon fusion, oxygen fusion, carbon fusion. So just like we had with the asymptotic giant branch, but now we have lots more different options of things that can fuse with each successive round of red supergiant phase. But once you have iron, you've run out of options. For iron, it has the highest binding energy of any element, and so once you've got iron, it can no longer make energy by fusing. It's not that you can't fuse iron, you can, but it will take energy rather than release energy. And so once you've got to that point, it must contract and heat up. Now, the temperature of the core at this point, having kept going through these successive phases, is about 5 billion Kelvin. So there's lots and lots of gamma rays around. Remember, this is Wien's law, so you have lots and lots of gamma rays around, and so you actually get photodisintegration of what's in the core. And so the iron will convert itself into lots of heliums and some neutrons, and in fact the heliums will also break down into hydrogens, which will break down, into neutrons and protons, basically. And so now you've got lots of protons and neutrons that are no longer bound to anything, and they're collapsing because they're not making anything else. They collapse so close together that the protons combine with the electrons to make more neutrons. You have lots and lots of neutrons, and they keep on collapsing. And so we've got, like I said, the silicon burning only lasts for about a day, and then it will just collapse in on itself, and it will take a very short time. So this is putting it in perspective. Like I said before, those cartoons we had weren't scale. In the core of this huge star, you've got all of these things with this tiny iron core. And what happens is, so you've got this iron core, it then disintegrates, and the protons and electrons combine, and you've got neutrons, and they keep getting smaller and smaller and smaller, until eventually the neutron degeneracy hits. So remember, the neutron is a fermion. It will not be able to be closer than a certain size, but that's a much smaller size than the white dwarf. But eventually it gets to a point where it can't get any smaller. But then all the outer layers are still falling in. Remember, you've got all these outer layers of things that are doing fusion, and then you've got all these outer layers that are just mostly hydrogen and helium, and they're all falling in onto the core, and so they bounce off. And so what you get is, in less than a second, you go from having these things collapsing down to causing all sorts of disruption, and the whole thing bounces back out. And this is where you get a big explosion. But the amount of energy, kinetic energy that's input, means that you're actually doing fusion in the exploding material very effectively. And so you're making things that are decaying radioactively, and so you get a very bright event. So you've already seen this image when we did the distance ladder, but this is how bright a supernova can be. It can easily, it's typically of the order of the brightness of a whole galaxy, so billions of suns. This is showing you how they look before and after. So this was in the 1987A supernova in the Large Magellanic Cloud, which can be seen from the southern hemisphere. This is what the star looked like before, and this is what it looked like when it was at maximum. And you can see there's a huge difference in the brightness. And this is actually the remnant of that object, and so so this is the image that we've got of it, and this is kind of a model of what we think is happening. So you've got this ring here as this ring, and we're kind of looking down this barrel so that we're seeing these two rings here. So you've got material that's flowing out in this kind of bipolar shape. Exactly why you get this shape is still not really understood, but you're also making lots of X-rays and all sorts of things. And these, just like the AGB stars, these objects lose material and have dusty clouds around them, and so that gets swept up when the supernova happens, and that will also give rise to some interesting shapes. And so here we've got, this is the Crab Nebula. You can see that this is actually a supernova remnant, and the supernova was observed by the Chinese nearly 1,000 years ago. This one is called Cygnus Loop. That's another famous nebula. And the Veil Nebula. And these are all what's left over from previous supernovae. Here you can see this is Cassiopeia A. This is what it looks like in optical light. This is what it looks like in X-rays. And so we can use these different wavelengths to look at what they're made of. And what you're left with then is a neutron star. You have something that is what's left over. You've got the iron that was in the core that is now disintegrated, turned into neutrons, and it just stays there. And so here's kind of a schematic of, if you have very low mass stars, you get white dwarfs that are helium. If you have intermediate mass stars, you get the helium flash, you get a planetary nebula, and you still get a white dwarf. And then if you have a malmassive star, it becomes a supergiant and makes some heavier elements, and then becomes a supernova and a neutron star. If it's really heavy, it will actually make a black hole. That is to say that your neutron star gets so compact that light cannot escape from its surface, and you get a singularity. And so you get those outer layers blown out, and you're left behind with something that is either, if it's a neutron star that you can actually detect, it is a few solar masses. It is 1.4 to 3 solar masses. If it's above 3 solar masses, it will be too dense, and you will get a black hole. And that's pretty much all I want to say about high mass stars. You should feel free to bring up discussion topics on these issues. So just to finally summarize the evolution of stars, here I've got everything from the lowest mass to very high mass stars. At the lowest mass, again, we get red giants, no helium burning, we may or may not get planetary nebulae, and we get a white dwarf that's made of helium. For the intermediate mass stars, we get red giants, we get a helium flash, we get AGB stars and planetary nebulae. At the higher mass end of the intermediate mass, you still get red giants, but the core is hot enough that you don't get a flash, but you still get helium burning. You get AGB stars, planetary nebulae, and white dwarfs that are still made of carbon. And then we have higher mass stars that are always supergiants. They stay as supergiants even though they're changing in temperature, and then they blow up and become supernovae, and then you're left with either a neutron star or a black hole. And so this is their mass in the main sequence. So if they're above about 8 solar masses, they're going to end up as neutron stars or black holes. Below about 8 solar masses, they become white dwarfs. And here you can see what the remnant masses are. So the white dwarfs are below about 1 solar mass, neutron stars up to about 3, and then above 3 you're going to get a black hole. And that's it for